Now, I know all three of you in this class are graduating this term, or that's my understanding anyway, if you can pass your math classes, but never, that's beside the point. But the other thing is that you won't be returning to Lawson in the spring. So all the stuff about registering for spring term doesn't really pertain to you, except for the fact that you know other students who will be returning in the spring. So please encourage them, if you can, as you can, to take advantage of this week. If they want face-to-face help, this is the week to get it. Starting yesterday and going through Thursday, from 9 in the morning until 7 in the evening, there will be people in the Academic Success Center on the Birmingham campus. That's on the Birmingham West campus, technically right across the street from Birmingham East campus, to help people with advising and registration. I know you won't need it, but others might, so please let them know. And then on the Bessemer campus, it's in the Ethel Hall Auditorium. Now, that's not to be confused with the Ethel Hall building on the Birmingham East campus. There is one there too, but this is the Ethel Hall building on the Bessemer campus. Their auditorium is up on the main level, which is the upper level. So best if you drive in the student parking lot down there, walk around the right-hand side of the building and come in the main entrance there, and the auditorium is immediately on your left. If you go in through the parking lot level, there's several doors that you can go in there, but then you have to wander around down there in a maze of hallways trying to find either the stairwell or the elevator, and it's so much easier to walk around on the outside, get up to the upper level and come in those doors or auditoriums just to your left. If you're on campus, please wear your mask. Please practice social distancing, when you're at the tables, there'll be plexiglass between you and the advisor or the whoever is there helping you. So, best to encourage people to do the virtual advising center and register themselves at home in the comfort of your own home and not be exposed to somebody. But if you really need the help, those two places are available for the rest of this week through Thursday, 7 in the evening. So 9 in the morning to 7 in the evening. Now, I'll try not to repeat that when the others come in, if they come in, but I'll refer them back to this and say, listen to this, because all three of you are leaving. Now, if there are no questions, we left off last time, Chapter 4, Vector Spaces, and Section 4.1, the title of which is Vectors in Rn. That's the real number system raised to some power, is how it is expressed. In other words, to some number of dimensions. Now, we've been talking some about linear combination of vectors, okay? And this is on page 158, top of the page there. An important type of problem in linear algebra involves writing one vector x, okay, vector x, as a sum of scalar multiples of other vectors v1 through vn, okay? So say that x is equal to c1 v1 plus c2 v2 plus c3 v3 plus dot 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 all the way up to some cn v sub n. Okay, that's what we mean by vector x being a linear combination of these other vectors v1 through vn. Now, is there anything special about the v1 through vn? Not necessarily, but there will be times when there's something very, very special about those. We'll be talking about this a little bit later. If these vectors are, I don't want to say a unique set of vectors, but one of a group of unique set of vectors, that's not quite making sense, but that defines what we call a vector space. There'll be a name for that. We call it spanning a vector space. If these n vectors are unique, are vectors in Rn, that none of them are linear combinations of each other, they're all linearly independent of each other, then any other vector in Rn can be written as a linear combination of those n vectors. Okay? Now, without requiring any of what I just said to be true, let's do example 6. Okay? So I'm going to clear this just to give us all the room we need. Okay? Here is vector x. If I could find my pen now. Where did you go, pen? There you are. Okay. Here's vector x. And this one happens to be in 3 space, which is where I live. Okay, so I feel pretty comfortable in this one. -1, -2, and -2. Okay, here is vector u. I have to write slowly or the pen goes just absolutely nuts. 0, 1, 4. And sometimes it goes nuts even when I'm writing slowly. Here's vector v. This is such a pain in the neck. -1, 2, negative, yuck! -1, 1, 2. Such a pain. Okay. And vector w is 3, 1, 2. Okay, I think I finally got it. They're all in R3. Obviously, they have 3 components. Okay, all members of R3, 3 space. Find the scalars a, b, and c such that vector x is equal to a times u, vector u, plus b times v, vector v, plus c times w, vector w. Okay. Now, there's no guarantee, absolute guarantee, that there are such A, B, and C, but since they say find them, they presume that there are. There certainly are vectors, u, v, and w, which that would be true, and I'm guessing these are 3 that it would be true as well. But what you can do, if you'd like, is just write it down just like we know it. -1, -2, -2, that's vector x, is equal to a times 1, 0, 1, 4. That's vector u, plus b times vector v, which is -1, 1, 2, plus c times vector 3, 1, 2. Now, what that basically does for you is, you know that to add vectors together and scalar multiplication as well, a times 0 plus b times minus 1 plus c times 3 would have to equal 1, negative 1. Has to, because the first components must add up to be the same. Okay, so I'm going to rewrite that statement I just did as 0 times a minus b plus 3c, it's dealing with first components only, is equal to negative 1. Similarly, a, that's 1 times a, plus b, 1 times b from here, plus c has to equal negative 2. Okay, and similarly 4 times a from here, plus 2 times b, plus 2 times c is equal to negative 2. All right, there we see 3 equations, 3 unknowns. Hey, we can deal with those, can't we? Now, because I have a limited amount of room here, I'm going to skip a bunch of steps and combine some things. In order to solve this, I'm going to write this as a augmented matrix that we can solve pretty easily using good old Gauss-Jordan or Gauss-Jordan elimination. It's pretty easy to do. Now what I'm going to do, I'm going to be very selective here, and I'm going to first rearrange, because the first thing we want in Gauss-Jordan elimination is a 1 in the upper left, and we've got a 0 in the upper left. So I'm going to swap these two rows as I write them, or these two equations, as I write them as a matrix. Okay, so here's what I'm going to do. Already swapping to, this will be a 1, 1, 1, negative 2. Okay, that's writing the second row. The second equation here is the first row there. And then I'm going to write the first equation as the second row here. That's going to be a 0. That's going to be a minus 1. That's going to be a 1. That's a 3, sorry. I'm jumping ahead of myself. And that's going to be a minus 1. Okay, now I'll look at that fourth equation and I say, I see a factor of 2 everywhere, so I'm going to factor that out. Okay, and that's going to be a 2, 1, sorry. 1, 1, minus 1. Okay, so that's where I'm going to start. Okay, so the first thing I'm going to do is a minus 2 times row 1 and add it to row 3, because I want to eliminate that and make that a 0. Okay, so doing that, I'm going to write down the first row again, 1, 1, 1, minus 2. Write down the second row, 0, minus 1, 3, minus 1. Write down, well, calculate my new third row. Negative 2 times 1 plus 2 is 0, of course. Negative 2 times 1 is negative 2 plus 1 would be a minus 1. Negative 2 times 1 would be a negative 2 plus 1 is another minus 1. And minus 2 times minus 2 is plus 4. Minus 1 is plus 3. Okay, check my work. I'm not doing too well today. All right. The next thing I want, I've got a 1 here and zeros below it. I want a 1 here, and then later it'll be zeros above and below it. Well, I've got a minus 1 there. So I'm going to again cheat and just make this a plus 1 minus 3 plus 1. Okay, I just multiplied everything in the second row by -1, which is legal in most states. Okay, now what I'm going to do next, I'm going to be pretty lazy about it and go on and do Gauss-Jordan elimination. I could just do Gauss elimination. I'll do Gauss-Jordan. So I want, actually what I'm going to do now, and this doesn't seem fair, but I'm going to do it anyway. Okay. I should have done it ahead of time. Okay. I'm going to undo what I just did. Okay. That was a minus plus minus. Right? -3, yeah. Okay. I'm just going to add these two rows together. I find it easier to do that than change signs, multiply, blah, blah, yeah. So let's just add them together. So first is going to be row 2 plus row 1. Okay. Now is my phone making noise? I don't see so. The only reason I paused to check, I wanted to make sure neither one of the other two guys were trying to get in. That's one reason. The other reason is our furnace is out downstairs. We have a unit up here that's doing okay, but it's not doing as well as it would if we had help from downstairs. So I want to make sure the guy wasn't coming to, he's not supposed to show up until 1, but just in case he was doing. So let's do the top up there. Now I don't have a lot of room here, but I'm going to try to make it work. Okay, adding row 2 to row 1. That gives you a 1, a 0, a 4, and a -3. Okay, then we'll write down the I'll write down the negative next. Okay, that would be a 1, -3, no, I'm sorry, 0, yuck. I hate doing this. This eraser is such a pain in the neck to get to work. Okay, sometimes. Okay, that's a 0, 1, -3, 1. So also did that. Now I'll do that here, making this a plus, minus, plus, and then I'll add row 3, row 2 to row 3. That's supposed to be an R, but it doesn't look like it. And that would be a 0, a 0, a -4, and a 4. I hope I'm doing this right. I'm skipping so many steps. Okay, obviously the next thing is to make this -4 a 1, do that by dividing by -1. Okay, so I'm really tempted just to stop right there. Okay, make this a 0, 0, 1, -1. Okay, and I'll write down the others. 1, 0, 4, -3, and this will be a 0, 1, -3, 1. This tells me that C is equal to -1. Remember, the third column here represented the coefficients of your C, so this is 1 times C is equal to -1, so C is -1. Okay, with that in mind, I'm going to do sort of Gauss elimination now, back substitution. If C is -1, -3 times -1 is 3. So this would be B plus 3 is equal to 1, which implies that B is equal to -2. Okay, and here we have A -4, that's what C is equal to -1, is equal to a -3, so A has to equal 1. Okay, when you add 4 to both sides. So I get A is equal to minus 1, B is equal to A is equal to 1, B is equal to minus 2, C is equal to minus 1. Let's see how the book did. 1 minus 2 minus 1. Perfect. Let's see if that works. Okay, let's see if minus 1 minus 2 minus 2 is equal to 0, 1, 4 minus 2 times minus 1, 1, 2 minus 1 times 3, 1, 2. Let's see if that works. 0 plus 2, that would be 2, minus 3 would be a minus 1. Sure enough, that minus 1 checks out fine. Let's do the next one. 1 minus 2 would be a minus 1. Minus 1 is a minus 2. That checks out perfectly. Let's do the next one. 4 minus 4 would be 0 minus 2. Sure enough, that's a minus 2. Those are how we can do a linear combination of u, v, and w to get vector x. We've done it. And I had a little bit of room to spare even, so we managed to get that done. Now, there's also a discovery just to the left of that. Is the vector 1, 1 a linear combination of vectors 1, 2, and negative 2, negative 4? It says graph the vector, and you're explaining your answer geometrically. You don't need to do that. If you just look at vectors 1, 2, and negative 2, negative 4, you see that negative 2, negative 4 is a scalar multiple of 1, 2. Just multiply 1, 2 by negative 2, and you get negative 2, negative 4. And since 1, 1 is not in line with either one of those, and they're just multiples of each other, it can't possibly be a linear combination of them. Now it says, similarly, determine whether the vector 1, 1 is a linear combination of the vectors 1, 2, and 2, 1. That one I would say probably yes, just because neither of those two, the second two, they're both independent of each other, and they're both independent of 1, 1, so you should be able to write that. And they say graph those. I don't think so. I'd say do it the same way we just did. So let's do that, since that I don't think will be too big of a problem to do. And I don't know how my cords get so tangled when I'm not really doing anything with them. So I'm untangling cords here, trying to anyway, and that's sending, I don't know what kind of messages across there, but anyway, I think I've got it untangled now. So let me clear my writing here, and let's do that second one. Is 1, 1, why the pen is just jumping all over the place. Carol, what did you do with the two guys? They're not showing up anywhere. One problem is I have my Wacom upside down. Okay, let me see if I can get it to work now. Yeah, there we go. Is 1, 1 a linear combination of, in other words, A times 1, 2 plus B times 2, 1. Okay, now in the future we're going to call these C1, C2, C3s. They're using A, B, and C now. It doesn't matter what you call them. They're just scalars. Okay, so this says just writing this down. A plus 2B is equal to 1, and 2A plus B is equal to 1 as well. Okay? Now, there's multiple ways to do this. Your augmented matrix is just as good as anything else. 1, 2, 1, 2, 1, 1. Let that be your matrix, and do a minus 2 times row 1 plus row 2, and that gives you 1, 2, 1, 0, because minus 2 times 1 is minus 2 plus 2 is 0. Minus 2 times 2 is minus 4 plus 1 is minus 3, and minus 2 times 1 is minus 2 plus 1 is minus 1. Okay, it's not going to be pretty, but it's doable. We'll divide everything by minus 3, and that gives you 0, 1, 1/3. Okay, and this is 1, 2, 1, and we'll multiply row 2 by negative 2 and add it to row 1, and this will give you 1, 0, and minus 2/3 plus 1 would be a 1/3, and 0, 1, 1/3. So it looks like the two constants need to be 1/3 each. Let's see if that's right. This will be 1/3, 2/3, plus 2/3, 1/3. That would equal 2/3 and 1/3 is 1, and 1 2/3 and 1/3 is 1. Yep, that works. Okay. Now, they say, what is the geometric significance of 1 and 2? Well, in vector 1, in question 1 in discovery, they were collinear. So they couldn't add to be a vector not on that line. Okay. Number 2 were not collinear, and therefore they could add to be a vector that's not collinear with either of those. Okay. Is every vector in R2 a linear combination of vectors 1, -2, and 2, and -2, 1? The answer to that is yes, because those are not collinear vectors. And so any other vector could be a linear combination of any two non-collinear vectors. That's our conclusion there. Now they have a little blurb at the bottom of the page. Sorry. It says you'll often find it useful to represent a vector u as u1, u2, u3 up to un in Rn as either a 1 by n row matrix or an n by 1 column matrix. Okay, or column vector, row vector or column vector, they mean the same thing. This approach is valid because the matrix operations and of addition and scalar multiplication give the same results to those, and I can't see there's any reason to go on about that. Okay, they said the only difference is how the display looks, so I'll Just leave that alone. You can read that. I think you'll see it makes sense. That finishes 4.1. Homework exercises here would include number 1. That can be found at calcchat.com. Either 3 or 5. Excuse me. It's either hunger or anemia. I'm just running out of steam here. Hold on just a second. Oh, wait. Here's James. I don't know how long he's been sitting there. Hopefully not long. Let me get James in here. So the top 2/3 of the class are here. We're just missing the bottom third. Okay, and hopefully Jesus will be here too. Okay. Hold on just a second. Okay. James, welcome. We are I'm making assignments for the 4.1 exercises. We just finished 4.1 in the text. And those exercises were, this is on starting on page 159. Example 1 should be at CalcChat. 3 or 5 should be at CalcChat. 7 or 9 should be at CalcChat. 11, any of the odds 11 through 17 should be at CalcChat, or actually 11 through 15 should be at CalcChat. 17 should be at CalcChat. Any of the odds 19 to 23 should be at CalcChat. 25 or 27 should be at CalcChat. 29 or 31 should be at CalcChat. 33 should be at CalcChat. 35 or 37 should be at CalcChat. 39 should be at CalcChat. Any of the odds 41 to 45 should be at CalcChat. And 47 or 49 should be at CalcChat. Over on page 160, 51 should be at CalcChat. 53 should be at CalcChat. 55 should be at CalcChat. 57 is a true-false. It should be at CalcChat. 59 is a writing exercise. I don't know if you'll find anything of special interest there for your research. I think you've already turned in, well, if you have or haven't, that should be at CalcChat. In fact, I would say any of the odds 59 through 63 should be at CalcChat. 65 or 68 should be at CalcChat. Okay, that done, let's move on to 4.2. Now, the title of the chapter is, Chapter 4 is Vector Spaces. The title of Section 4.2 is Vector Spaces, the same title. The objectives here are to find a vector space and recognize some important vector spaces and show that a given set is not a vector space. So one part's fairly positive, one part is a little on the negation side of things. So we start with the definition of a vector space. Now, I'm going to clear what we've got here. Anyone need this a little longer? Okay. Now, I'm just making an assumption that James got in here because I haven't seen him pop up yet. Yeah, I see. Yep, he's here. Good. Okay. Sometimes all the pictures show and sometimes, or the rectangles show and sometimes they don't. I don't know why Zoom does it one way one time and another the other. Now, we just ended that section talking about vectors. Vectors, you know, a linear array of something, you know, vectors. Now we're talking about vector spaces, and all of a sudden we're going to expand our definition of what a vector is and what a vector space is. Theorem 4.2 lists the 10 properties of vector addition and scalar multiplication in Rn. Remember, it was just like Theorem 4.1, which did it for R2. 4.2 did it for Rn. That was back on page 156. Okay? Now, dealt with vector addition, which includes subtraction, by the way, and scalar multiplication, okay, in Rn. Suitable definitions for addition and scalar multiplication reveal that many other mathematical quantities, okay, this is where it gets a little bizarre, such as matrices, follow those same 10 rules, okay? Polynomials follow the same 10 rules. Functions follow the same 10 rules, okay? They also share those 10 properties. Any set that satisfies those properties, and they call these axioms, it seems like to me it should be axia, but you know, they're sort of mixing their Greek with their English, is called a vector space. And the objects in the set are vectors. So all of a sudden, from 4.1 to 4.2, the whole concept of a vector as a directed line segment, it still is. Those are all vectors, but now we expand the term for vector to include things like matrices, polynomials, and functions. And you'll find we do other things as well, but those are the big ones, okay? And we'll call those vectors, and we'll call their spaces vector spaces if they meet those 10 criteria. It is important to realize that the definition of a vector space below is precisely that. It's a definition, okay? You do not need to prove anything because you're simply listing the axia or axioms required of vector spaces. This type of a definition is an abstraction because you are abstracting a collection of properties from a vector setting or N to form the axias or axiom for a more general setting. Okay, whatever that means, okay. So, here's the definition of vector space. Now, remember when we used capital letters to represent matrices, usually the letters A's, B's, and C's, okay? We also got into the habit of using bold letters to represent vectors. Those are our directed line segment vectors, okay? That's still good, okay? Now we're going to be talking about a vector space, okay? So we're going to go back to capital letters, and a lot of times they will italicize these. Guess what? I can't write in italics. But whereas a matrix was usually A, B, and C, the vector spaces are usually going to be capital V, capital U, capital W, things like that. Though there will be others that we'll use. And that's how we'll represent vector spaces. Their favorite being V for vector space. Now notice that doesn't have bold. It doesn't have an arrow over it. It's a vector space. It is not a vector. It contains vectors, but it's not a vector itself. Now what it is a set. A set. A set can be any collection of anything. So a vector space is a set. Now not all sets are vector spaces, but all vector spaces are sets, okay? A set on which two operations, just two, that's vector addition and scalar multiplication, are defined. Now here's where they throw little wrenches in the system. Most of the time we know exactly how a vector addition and scalar multiplication are defined, but guess what? They'll sometimes come up with an alternative definition and say, is this a vector space under these rules? Sometimes they will be, sometimes they won't. So they like throwing little wrenches into the plan here, okay? If the listed axioms are satisfied for every vector, now they're going back to naming vectors, lowercase u, v, w, those kind of letters, bolded, okay, so that means I have to write arrow over them, but these are for every u, v, and w in the vector space capital V, not bolded, generally italicized, but I guess it doesn't have to be, and every scalar, which is a real number, C and D, then V is a vector space. So here are those 10 all over again. Okay, definition of a vector space. Okay, goodness gracious, I'm just running so low of energy. I hope I can make it through. All right, let me get these. Okay, so I'm going to get you used to seeing me write it. Okay, let V be a set. That's how I'm going to write the V, capital V, on which two operations and that's vector addition that's supposed to be vector addition. This pen is all over the place. And scalar multiplication this writing is terrible. Okay, are defined. Okay. If the listed axioms for every vector uv are satisfied, this is terrible writing, for every u, and these are vectors now, in V, and these are elements of that vector space V, or that set, is right now a set, elements of V, and every scalar and this will be, those are real numbers, C and D, C and D, not C and C. Okay. Then, if all that is met, then we say V is I'll abbreviate as vector space. VS means vector space. All right. Here are the 10 axia. You've seen them before. Okay. U plus V, this is your addition, are also in that vector space or that set V. Okay. I'm tired of holding the book, but it's hard to read without it. This is called your closure under addition. Okay, now your addition rule, whatever that is, that's in play there. Okay, number 2, it doesn't matter the order. U plus V is the same as V plus U. Okay, that's the commutative property. Terrible writing. Of vector addition. This is terrible. That's, the writing stinks. Okay, number 3. If you have 3 vectors added together, it doesn't matter which order you do them. U plus, if you added V plus W first, then you would get something that's the same as U plus V I can't get my pen to be agreeable here, plus W. Okay, so it doesn't matter the order in which you add those 3 vectors. Now, part of my problem here, I don't know why it happened yesterday too. I think I do know why. I told you my furnace was out. Well, maybe James, you didn't hear it, downstairs. And the morning starts fine. It's colder outside than it is, later in the day. But I'm on the northeast corner of the house, and once the sun quits coming in this room, it gets chilly. So I'm going to pause for just a moment here so I can go out in the hallway and turn up the thermostat just a bit. The upstairs furnace heat pump is still working. So hold on just a minute. I'll be right back. Hold on.